Oscillators, a basic training by me, Nick Amey. So in this slide, I want to cover the basics of how to specify an oscillator. Let's assume you want to buy an oscillator and you approach a company like ours and you ask, I want an oscillator. What are the basic questions we're going to need to do between us? The first one, of course, is you ask for something that gives a frequency, so we better establish what frequency you want. And a low-cost commodity oscillator is available in a really wide range of frequencies because we're simply going to grind and lap the crystal and that will give us a frequency that you require. A high-performance oscillator, when you start looking at OCXOs or even TCXOs, the technology behind getting a really stable frequency becomes a lot more complicated, so the range of frequencies that I can offer you is a lot more limited. But nonetheless, we need to establish what frequency you want. Supply voltage might be the next thing that we need to talk about. Oscillators run on electricity, so we need to know what supply voltage you're running at. Normally that might be 3.3 volts or 1.8 volts or something like that. The supply voltage to an oscillator is going to need to be very, very stable. Any noise on the power rail is going to translate directly into frequency modulation on the output. So I'm hoping that you've got a very stable power supply. And then when you come to ovenized oscillators like OCXOs, they're running a lot of power. It might be something that you want to consider. Maybe you have a 12-volt line on your power supply that you weren't using, and maybe that's going to be an isolated power supply for an OCXO and give us the extra current that we need. Talking of power, yep, warm-up time and steady-state power. If you're using an OCXO, then it's going to draw a lot of power for the moment that it's warming up, and then there'll be a different definition for the power once it's in steady-state operation, as we call it. So the example on the right there shows a product which has a need for 800 milliamps at 3.3 volts for 5 minutes while it's warming up, and then after 5 minutes that will have dropped down to 350 milliamps. That'll be a decay curve, it's not a stepped transition there. I have had a situation once where a customer had a power supply and it didn't quite have enough to give the full range at the moment that it warmed up, and that meant that at the moment it warmed up the rubidium was struggling because different parts of the system were not seeing the same power, and so it never really hit a stable state in its operation because one part had started before another part because it didn't have the right power for it. So there's some lessons to be learned from that. The next conversation we have could be about the output type. It's an oscillator, it's going to make an output switch on and off, but do you need that output to be a really nice clean square wave like a sine wave? Seems obvious, doesn't it? Except that square waves contain a lot of rising edges which can be very noisy in high frequency areas, so you might want a sine wave. Sine wave would be the purest frequency wave that we can give you. Or maybe you're using a really high frequency and you're looking for a differential pair, something like an LVPECL or an LVDS output, because that's going to help cancel out the noise in the high frequency and give you better transmission lines over your PCB. Then we come to frequency tolerance. Frequency tolerance is a phrase we use to mean the measure of how accurate the frequency is when you first put the device onto the PCB. So we would normally measure that at 25 degrees. As you saw on the curve on the earlier slide, that's because that's the rollover point for an 80 cut crystal. So we're going to discuss how accurately, how close are we going to hit that original frequency that you asked for when you first put the product onto the PCB. And that might be something like 0.05 parts per billion at 25 degrees or something like that. This tolerance can be removed using a pulling function. So if you're using a VCXO, as we showed in the other circuit, you can put it on the PCB and then you can adjust a calibration pin, if you like, and you can pull that frequency up or down to bring it into spec. The next parameter we might discuss is called frequency stability, and here we're talking about the change of frequency as caused by temperature. So now we're looking at that curve that we saw for the 80 cut crystal and how that's going to behave. As I said, I can change that curve a little bit by changing the angle that we cut the quartz at, and I'm going to try and hit your requirements but I'm also going to try and hit your budget. So how tightly do we need to control that? And we might say something like 0.3 ppb typical over 0 to 70 or something like that. So we're going to have a temperature range and a frequency stability in the combination there. Which brings us to the next one, temperature. And yep, we're going to need the range to be defined. You need to be careful with these products. A lot of other electronics products are available in very standard frequencies. So you might have -40 to 85 as a commercial temperature range. And that's fair enough if that's what you really need. But bearing in mind for quartz crystals, there's a direct relationship between the physics of how it works and how it happens over temperature. So if you really don't need -40, if you're working in something like a server cabinet and you're never going to see temperatures below -10 or even +10 degrees, and you're never going to see temperatures above 70 or 80 degrees, then that's a much reduced temperature range for us to control behavior over. And that's going to make the product easier for us to design. So that is going to have an effect on the cost for the product. Then we have pulling. So we talked before on the VCXO about having that input where we can change the frequency as we're running the device. And if we're going to use that function, we're going to need to define it. And we might define it on an OCXO as something like ±2 parts per billion as a minimum amount that you can pull the frequency. And we'll give you a control voltage. We might have an input pin and we say, look, the midpoint could be 2.5 volts. And then you can pull it to +2 ppm if you go up to 5 volts, and to -2 ppm from what it was if you pull it down to 0 volts or something like that. I did have a colleague that discussed the idea of an oscillator that didn't have enough pulling to overcome its own aging, which I can see being a problem. So if a product has got an aging specification and you're going to run it for 10 years, you better have enough pulling over that 10 years to be able to remove all the aging that it's going to have. I would say that 99% of the products I've ever seen would be able to achieve that, but I have heard a story about a product that didn't offer that, which was a bit of a surprise. And then finally for this slide, we're going to talk about digital control. So an oscillator is just going to run, make you a nice stable frequency, but you might want some control mechanism over that. And at the very basic level, that could be a digital control pin that when it's high, the oscillator is running, and when it's low, the oscillator stops, something like that. In that case, I would still ask the question, when you say stopped, did you mean that you wanted the output buffer to disable, but the internal oscillators to keep running, meaning there's no output available, but when you need that output, you can switch it back on very, very quickly because internally I'm still running. But therefore the current draw, when you switch it off, is going to be about the same because I'm still doing the same amount of work internally. Or alternatively, would you have a function where you can switch off the internal oscillator? That would massively reduce the current draw from milliamps down to microamps. But when you switch it back on, you might need a few milliseconds before you have a stable oscillation again. So something to think about there. Other oscillators like OCXOs have functions like lock pins to tell you when the internal lock has been established. They have pins that tell you as an output to say my temperature is now stable and things like that. So other forms of digital control. In this slide, I want to talk about some of the more advanced features of an oscillator specification. So in the last slide we talked about the basics that we would need to establish between us, and now we're going to go into some of the more complex areas of how an oscillator works and how we define it. So let's look at aging. We've talked already about the fact that quartz crystals might change frequency over time, and we call that aging. What's happening there normally is there's a stress relaxation on the blank and some outgassing happening, and that causes a logarithmic decay of the frequency. So predominantly you're going to see more aging in the first few months or year of running the device, and then it will dissipate down to nothing. But nonetheless, you might need to define that, and it's normally on the specification, and it might be defined in how many ppb per year, or on a high-end product it might be in how many ppb per day, per month and per year. On from that, we have load coefficient. So this is a measure of the effect of the load of the output on the frequency of the oscillator. So standard oscillator circuit is trying to drive some input buffers. So the output from us is driving some inputs from you. We call that a load, and it could be represented as a capacitance, and we might say as standard we test things with a 15 picofarad capacitance hanging on the output in order to simulate the load of running your inputs. And if that isn't 15 picofarads, if it's a little bit higher, a little bit lower, then what's the effect on the frequency? Because it's going to have an influence, and there we might describe something like a 5% change in load, and it might cause so many ppm, 5 ppb or something, as a maximum change in frequency that you could expect. So that gives you an indication of what's happening on your PCB and why you might see a frequency different to the frequency that we told you it was going to be. Might be because there's a different load in your PCB to what we had in our test circuit as we designed it. The next one would be pushing. Pushing is an interesting term we use to describe how much the frequency changes when the supply voltage changes. So you could say it's a modulation of the frequency caused by the supply voltage change. One of the most common problems here would be noise on the supply voltage line. So if you've got some digital switching on the same line and you haven't got enough filtering, then that digital switching will translate into a frequency modulation that you're seeing on the output. And here again we might describe it as something like a 5% change in the supply voltage will cause so many parts per million in the frequency shift. Then we have shock, vibration, acceleration, and all the other environmental stresses that components have to survive. And we might well put on the data sheet something like mechanical shock as per IEC 68068 test 2227. We might define the level of shocks and the amplitude of the duration. And we will lay all of that out on the data sheet, and you might have some specific application where there's a specifically high shock that we need to meet or something like that. I've seen guys in the rail industry have got some very interesting shock causes caused by the vibration of very high masses on the rail. So we can do tests to prove that products can meet those specifications. It's worth thinking about when you look at that on a data sheet. Almost always that is survivability being defined. So we're saying that the product before and after those environmental stresses will still be within specification on the output. It's a different thing to say what will the frequency do during that shock and that vibration. So just be careful what you ask for and how you define it on the data sheet. Retrace is another one of the more advanced questions we might have. So retrace is a measure of how much the frequency changes when I switch the oscillator off and switch it back on again. Sounds a strange thing, but on an OCXO where the frequencies are parts per billion, it could be that it's just not quite the same, or it takes many, many hours until it's back to where it was. And so we would have a definition of retrace that might say something like, I'm going to run the oscillator 24 hours on, switch it off for 1 hour, switch it back on for 1 hour, and then tell you how much the frequency is close to what it was in the beginning. And it might be something like 0.2 part per billion or something. So we're talking very small amounts. On a standard SPXO, these things are not worth worrying about, but on something like an OCXO, it becomes significant. Same goes with gravitational force, this change of frequency caused by change of gravitational force. Might sound a bit strange, why would the gravitational force change? But we have what we call a 2G tip over test. So that would be where the gravitational force of the Earth is 1G, and if I turn the device upside down, then it experiences negative 1G in the same plane. So one minus the other makes for a 2G, and we call that a 2G tip over test. And therefore we can measure the frequency of an oscillator in one direction, turn it up the other way, measure the frequency again, and ask whether it's changed, and we can repeat that through 3 different axes. and define which axis gives us the maximum change, and therefore talk about how much change it is. The changes we're talking about here are tiny. We're talking 2 to the minus 12 per G, something like that. So again, it's only relevant on really high-end OCXOs, rubidiums, and those kinds of products. And the same would be said for magnetic field sensitivity. So changes in magnetic field sensitivity, especially on products where microwave cavities are used and things like that, are significant, they're measurable, and magnetic field changes due to large chunks of metal moving around, we can detect when lorries are driving past the lab in our site and things like that. And the frequency change you might observe caused by this could be, when measured, in the range of plus or minus 2 to the minus 11 per gauss. So again, very, very small stuff, but relevant if you're looking at stuff that's accurate, like a rubidium or an OCXO. So final point on this slide, those parts marked with a dot are things that cannot be removed, whereas those not marked will be corrected for. So you can use the pulling and you can remove the aging, you can remove the effect of the load variations because they're normally stable on your PCB. The retrace is known once the power's back up, but the other things are, you're going to have to live with them. So the other things that I've marked up there are things that you should be aware of. They're going to happen during its operation, and if the sum total of all of that puts it outside of what you can use, that's going to be a problem for you. Okay, so thanks very much. That was a brief summary of general state of oscillators across the industry, and hope for some insights into how they're manufactured and what to look out for them. There's some further reading here if you're interested, and we'll be doing a lot more of these in the future, so do check back for more.